Hi, I'm Felipe. I'm a lead developer at Spotify. I'm based in Stockholm, Sweden. And I work in the team responsible for the infrastructure of our desktop application. And today I'm going to talk about how we've been using JavaScript in our client. And I'll be sharing some of our architectural details and a bit of the stories of the things that we tried and worked for us, things that we tried and didn't work for us, and what we learned from them. So I've been chatting with some people here at the conference, and I realize a lot of people don't know that Spotify for desktop is based on web technologies, but it is. And right now, we do have a lot of native code, but the whole UI is web-based. So the goal of this talk is to present the story of how we got there and everything we learned in this process. But before getting into where we are today, I'd like to go back to the beginning of the Spotify history and describe the journey until now, like the evolution of the software, how it started and how it is right now. So it all started like 10 years ago. This is the first sketch of the idea. In 2006, two guys in Sweden had this idea that we needed to change the music market because piracy was taking over. We needed something that would allow people to consume music that would be just convenient, that they could use all the music, they could listen to all the music in the world, and they would just look like they were using their own library. And it should be an alternative to piracy. It should be convenient, safe to use, and free and fair to the artists, so they get paid by their music for them. And however, that idea came in 2006, but Spotify was just really released to users in 2008. And the reason for that was not just the technological challenges, but mostly the business challenges around that. Because Spotify was disrupting a market, and then it's a really traditional and big market where they have really conservative ideas of how things should work. So it was a long journey of negotiations and contracts with record labels and trying to get the idea that this model should work. And then this was 2008, more or less. And around 2011, Spotify had already grew a lot. It was mostly in Europe, had just opened in the US. And then there was a need both from Spotify and from other developers to build a community. So Spotify released a platform where third-party developers could write their apps and run them inside Spotify. So you could have things such as Last.fm, for example. You could use their recommendations inside the Spotify client and things like that. This platform is no longer available, but it is really important to the story I'm going to tell today. We changed the approach we have with third-party developers that for another model that works better for them and for us, that's exposing SDKs that they can use in their apps instead of having their code running inside our app. And in order to make that platform work and have something that other developers could work with, we started having web views inside the client. And for that, we use Ceph. Ceph stands for Chromium Embedded Framework. And it's not as popular as Electron or Node WebKit, but it's older than those. And what it does is basically the same, but it requires a bit more of C++ code to integrate. And then it allowed us to embed some web views inside the client. And it is an open source project that is used mostly by Spotify, but also for Steam, the gaming platform, and some products made by Adobe, and of course some smaller projects as well. So at the time we had this client that was mostly C++, but we had these web views that were just regular web pages. And in those web pages, everything was sandboxed. So from the developer perspective, they own the whole document. The whole DOM belonged to their app. They had the global scope for JavaScript. And they could use a JavaScript API to talk to the Spotify functionalities, such as playback control or fetching the user playlist and things like that. There was an API that they could use for that. And then we started dogfooding this platform internally and changing our internal views in the client to use this apps platform, and that's how I want to call those views from now on. They are apps. So for example, the artist view in the client is now an app, just like a third-party app that is HTML, JavaScript, and CSS, and use the same API. 2 years later, 2013, Spotify went through its first big UI change. Spotify went black. It was great, it went black, and then replacing all the C++ UI components was painful, mostly because we use some custom C++ UI libraries built in-house, and that's usually not fun. And also at this time, the first laptops with high DPI screens, or the Retina screens as they're called, starting popping up in the market. And you could start seeing differences when you open the client and the Retina screen, that the web views had support for that out of the box, but our C++ UI components didn't. So we could see some blurry text when it was a C++ view, and a really nice rendered text if it was a web view. So it was a bit complicated, but we kept this hybrid approach at this time. And then 1 year later, there was another iteration of the client, where we still had a very similar UI, but we had a really big difference in terms of the stack. We went full web. So all the UI code that was before in C++ was removed and replaced by HTML and JavaScript. And things that were done as regular C++ method calls became APIs exposed to the JavaScript layer that could be called from there. So now we have this client that's fully web-based. And for us developers, there was a big advantage of that, because it's, of course, much faster and easier to develop on it. And we gain some things for free by using this stack, such as the Retina support, as I said before, but also it's better for accessibility, because you can integrate better with screen readers for users with visual impairment and other accessibility issues. But then to get there, we went through a big dilemma that I think most developers in this room and outside this room have been through. So you have this big code base that works, and it attends your needs, but it's really hard to work with. Should we actually rewrite that code? It's usually an anti-pattern. You were replacing something that works and adding risks to it. You can introduce new bugs and all of that. And then also in this case, we had going to replace this big chunk of code, but there is no really any visible gain for the users, at least short term. So it's kind of questionable if it's actually worth it. And then like the old code we had, the C++ code, had been around for several years. It has been tested a lot. We knew that it worked well. If we just replace it with a new code base, it could be introducing a lot of new bugs. And it was, of course, the opportunity cost. So you were rewriting old code, and then you were missing the opportunity to build new features. And you can also block the development of new features because you were rewriting that old code. So there are several arguments not to rewrite code that works. So, and when you discuss in a team about rewrites, those discussions can be really emotionally charged because people can get attached to the code they wrote, and some people can also have can kind of hate code that they didn't work because they don't understand, because writing code is easy, but reading code is hard. And then sometimes when you get someone else's code, you can just throw it away and build it yourself. But you have to be pragmatic when you think about these things. And then we try to apply a bit of engineering thinking on that. And when I say engineering thinking, I mean that engineers should analyze trade-offs. They should look for optimizations, and they should look for improving the efficiency of the product and processes they're working on. So how could we do that in a way that we would be pragmatic about the trade-offs and try to optimize the cost and the benefits we're going to take out of it? So we thought that we would be, if you take this path and rewrite this C++ code in JavaScript, we would be adding value by allowing us to iterate faster in the future and experiment with things in the UI because you have a much more easier code to work with. And then as a data-driven company, it's really important for us to do A/B testing. And then it's nice if you have a code base that allows you to do that easily because you can iterate much faster. And on the downside, you had a really high implementation cost because you have to rewrite this whole code base. But we thought that it would pay off over time because the maintenance cost would be much lower. So we went ahead and thought that, yeah, let's do this. And what I'm going to talk about is a bit of the architecture, how we structured our layers and our architecture in order to achieve this goal. So I'm going to describe the architecture bottom up, starting from the lowest layer. So under everything, there is what we call the client core. And client core is a library that have at Spotify. That's a C++ library that's shared among all the main platforms. So it's the same code base for Android, iOS, and desktop. And what this library does is basically the lower level things, like it's responsible for the streaming, decoding, playback, audio drivers, talking to the backend, offline syncing, and all those things that are common between those platforms and are more integrated in a lower level. And above that, and then also like this client core is, as it's used by several platforms, the ownership is also shared by those teams. So the infrastructure teams of those platforms work together in this library. Above that, we had the client desktop layer. And what that is basically the integration with operating systems of Windows and Mac and Linux, even though Linux is kind of not officially supported. And what it does also is to glue together the core and expose things to the web layer that's above it. So that's what the client desktop does. And if you were yesterday in that really nice talk about Electron, she talked about two processes, the main process and the render process. Here it's pretty much the same. The two layers at the bottom are the main process, so we don't have any JavaScript running in the main process, but the render process are the rest at the top. So we have like the Chromium embedded framework that basically just renders our web views, and the client desktop exposes some APIs through Chromium embedded framework, so we can talk to core. And then we have two layers of JavaScript, where JS container is more like a logic layer, where we manage like navigation, playback state, and things like that for more the container of the UI of the UI. And the little boxes in the top are the actual views, the actual what we call the apps that are owned by different teams. So, for example, have the browse view or the search, the playlist, the artist. They're all like their own little boxes that belong to different teams. So if you want a more visual understanding of these JavaScript layers, more or less like this is how we visualize. And then we kept the same architecture for the apps as we did for the third-party developers a few years back. And so the container is the main Chrome, and the application, it manages all the apps inside it. And the apps are sandbox, as I said before, so they own the document, they own the global scope. And the way to do that was to use iframes. And then some people might be a bit surprised, like, come on, it's 2016, you're still using iframes. And of course, it's not ideal, but life is a trade-off, right? And then use iframes was a really pragmatic decision at the time, because iframes are a really cheap abstraction for sandboxing on the web. So we could guarantee, for some level of guarantee, that things are running there with their own environment, that didn't really leak things to other things. And it's not all negative, because imagine that Spotify is not really like most web applications that people run on the browser, and they close once in a while, or like after a few hours or something that people can leave the client open in the background for weeks. And then memory leaks can be a big thing there in the client side. And with iframes, we can, even though the iframe itself has a higher memory footprint, we can just kill iframes and then release that memory much more easier. So the feature developers that work inside that iframe, they don't need to care too much about that, even though they should care, but not too much, because the container can kind of manage, okay, this iframe has been idle, let's just kill it to release some memory and things like that. And keeping iframes when we did this rewrite reduced the risk of the rewrite, because the rewrite didn't affect the apps themselves. So like the people who were working in the artist field weren't affected at all by the process that we went by replacing the infrastructure, because they still kept their sandbox environment. So it's something that we used to reduce risk in this migration period, and you can iterate on it afterwards. So based on what I said so far, having these two layers of JavaScript, a lot of custom libraries and tools, how do we actually organize our code? And then this is something that we did, and seems really standard. So we had all those apps, so we had one repository per app, playlist, browser, everything their own repository. Had one repository per library, so we had some libraries internally, such as our UI library that has CSS and how buttons look like, and templates and things like that. We have another library that does the parsing of Spotify internal URIs and things like that. And we had an instance of an internal NPM registry to distribute these libraries. So it seems pretty standard, but no, didn't work for us, which is also can be surprising for some people. And why didn't it work? It's like every team had their little things that are organized. Everything seems really encapsulated, but why didn't it work? It was really hard to coordinate horizontal changes. And when I mean horizontal changes, it's like a change that affects many views. So suppose you were working in the generic UI library for Spotify, and then you want to change the shade of green that we display, or the behavior of the play button that is everywhere in the client. So you had to make the change in the library and make sure all the apps have new builds that fetch your new change. And so it involved a lot of communication and syncing between teams, and especially stressful before releases. It's a bit hard to coordinate. And that could also cause some cascade effect on library updates. So imagine you are changing a really basic library, that there is another library that depends on it, and another library, and an app that depends on it. You have to make sure that all the versions were bumped, and dependencies were bumped, and things like that. So the communication overhead was really, really high with this model. It also complicated continuous integration, testability, and standardization. It complicated continuous integration because the build pipelines needed to be changed somehow. So we wanted to make sure that if I change something, and after it builds, I want to also build the things that depend on it, because I want to keep consistency in my product. Even though semver is a good idea, it might have some things that we need to force libraries to be updated, so we need to trigger new builds of things that depend on my library. So if we actually needed it to work well, we would need to create a really complex graph of dependencies in the build pipelines. It's not something that you want to do. And for standardization, it's also hard because you're creating silos. So different teams will build things in different ways and use different tools. And that's it goes a bit with autonomy. That autonomy is usually good, but you need some alignment. And then this architecture, it makes alignment more difficult. So this is how it looked like. So suppose you have the playlist app, the radio app. They depend on the same libraries, but they depend on separate versions because they are in separate repositories. They are separate modules. So you have those things, and then every app had their own build pipeline. So when you build, you generate the artifacts, and you could, for example, have playlists with a different style for the track lists than in radio, for example, or a different shade of green in the same release, and that's not something we want to have. So we started investigating into it. How could we avoid this kind of problem? So we checked how other companies have been doing, how to merge repositories and things like that. So how could we mitigate those problems? So basically what we did is we jumped into the monorepo. We had merged all our repositories in a single one, and it automatically addressed a lot of the issues that we had before. It simplified a lot the continuous integration because we just have one build pipeline. You change the repository, you build everything, and it's fine. It's always it always works as it should be. And it's easier to test the impact of your changes. So if you're making changes in a library, you can just grep and see what it's being used and just fix it there. And because of that, you don't need to care about backwards compatibility, which makes the code much simpler. You don't need to keep old code there. Just make a change whatever it's being used, it's fine. And you can do that in an atomic way. So you can make a change in a library and the code that depends on it in a single commit, which makes it much easier to go back and forth and roll back and everything. So It is much easier for refactoring the code. And it promotes some consistency and standardization across the board, because all the code is in a single place. So now we had like this single repository, this single build pipeline, and we could have consistency in the dependencies because they're all fetching the same dependencies. So yeah, now things are much simpler than before. We have all the code in the same place. They are fetching the same dependencies. But there is still a lot of entropy, and the reason for that is we had many teams working in these little repositories. They're kind of siloed in their own worlds. So in order to scale our development and our teams, we gave them autonomy to pick their tools, to pick their technologies. And then when we started putting things together, we saw many things were different. So some teams used to write unit tests in framework A, another team's framework B, and when we started like putting everything together in the same build pipeline, come on, we need to fix this. We need to find a way to standardize our practices. So we came up with the idea of the golden path. And the golden path, what it is a set of recommended practices, tools and libraries that are fully supported, and that's the recommended thing that people should use. It doesn't mean that they're forced to use, but if they do, they get all the support from the infrastructure team, all the tooling. They can just focus on building their feature. They don't need to focus on spending time in tooling. Tooling is there. Just use it and build your feature. Of course, you can still go crazy and do other things, but yeah, it's not something that we would really like. So the way we came up, the way we started working in the golden path was to put together a standardization work group. And the way we did this, we got like one representative from each team. And this work group would get together and analyze different things that we had in our code base. So let's check all the testing libraries that we are using. So to make, we are using, for example, look at the unit test, and some apps are using expect, some apps are using assert, some apps are using whatever. And then, so how can we standardize on some things so we can go into all our tests and understand how they work and things like that? So this work group goal was to actually do this kind of analysis and come up with solutions and proposals for that. And when I started analyzing and building this golden path documentation, we started seeing some de facto standards that were easy to standardize on, because that's what most people were already using. So we just went ahead, okay, 80% of our code base already does it this way, so let's just do it for the rest. And so if that would be taking the path of least resistance, and so it would be easier to make everyone align in the same thing. And we try to make those decisions based on actual data. So we don't really want to go for wishful thinking. We actually want to have some experimentation around some technique or some tool, and then see, okay, that works for that team. Maybe we should actually adopt in other teams as well. So there were some lessons we learned in this process, so I'm going to just recap things that I said before and things that we learned when we got to this stage. That's the stage we are right now. We are aligning teams in same practices so we can move forward and maybe rethink the iframes thing, because once the code is more standard, it's easier to remove those kind of sandboxing and things like that. So one first thing that is really important is to, in your projects, always try to evolve things incrementally. And what that means is that don't try to solve all the problems at once. Try to fail fast and validate your hypotheses. And try to release as fast as possible so you can see the impact that you are creating. And also, like, many companies have an infra team, like the team I work. And in some companies, infra teams are usually kind of dictators that, okay, we've built this thing, everyone should use it this way. And for us, having more empathy, as we saw yesterday, and more connections with the other developers made things work much better, have a much better relationship with feature teams. And we can get things with much higher quality. So having an infra team that's more in touch with other developers and listening to them, and having other developers participating in the decisions have really improved our flow to get things working. And when we merge repositories, we noticed that the way we structure our repositories shouldn't dictate your architecture. So that's why for us, merging them was a good idea because it gave us a lot of flexibility on how we want things to change in the future. And last but not least, like consistency is really important in a code base, especially in a big project. It's more important to have one single way of doing things than doing like the coolest thing ever. Because when you have a consistent way of doing things, people are more productive. People can understand better the code. They can navigate through the code and see, okay, this is how you do it, and this is how it's being done. But if you're just focusing on trying like this new thing and make it the coolest possible, and then everything is different in different parts of the code base, it really makes it hard for people to understand their code and to, for example, when you got a new hire, you know, company is growing, you need to have okay, this is how you do things, and then this person is going to be up to speed much faster, and you have like such a heterogeneous code base. And yeah, I couldn't miss the opportunity with so many good people here to say that we are hiring. So we've been through a lot of challenges, have a lot of challenges ahead. So I recommend just take a look at our jobs page, and the job ads there are usually pretty vague and open, but if you need more details, you can just grab me and I can give you more details. And that's it for me.